Okay, this is the summary video for 1.4 about function transformations. So these were the board notes that have been in Schoology. It's what we discussed in class. We talked about how there was a times whatever the function is, but then the function is of x minus h, and then the plus k, and what each of those letters sort of does. Now it's important to recognize that this p of x that we've inserted this minus h, the plus k, and the a times around can be any of the 10 parents that are on that sheet, or absolute value. So technically 11 parent functions. There's two ways to think about this. One of them is, given a function, can you graph it? But as you saw on the quiz for 1.4, the test-like question is going to be, given a graph, can you come up with the function? Can you identify the transformations from the graph and come up with the function that must have made it? So we spent some time in class going from an equation to a graph. And that's a little bit easier because we could just make a table if we know how to do the operation. Or we can identify the transformations if we know what the shape of that function is. So I'm gonna do that briefly, and then we'll talk about how to reverse that and how we can use the same thinking in reverse to get from the graph, identify the transformations, and then generate the function. Get some more practice with that. So an example function might be f of x could be, let's go with let's do a exponential function. We're going to do 3 to the x plus 2 plus 5. Okay, so this exponential function has an inside, meaning something happening to the x directly, and this is an invisible grouping symbol. The fact that it's in parentheses, or that it's up in the superscript, means that it is essentially within parentheses. If I were to plug a number in here, I would have to add the 2 before I considered raising 3 to that power. So that is a grouping symbol, and that means that we are inside the function if we are up in the exponent. These sort of hidden grouping symbols can include the fraction bar. Anything below the fraction bar or even above it is considered grouped together, and that division can only happen once you've simplified the top and the bottom. The radical is a grouping symbol. These are a little bit more obvious. The logarithm has an obvious sort of parenthesis around it, but it's really this one and that fraction that are the hardest to sort of understand. Inside means within the invisible grouping. So up in the superscript is a grouping, or down below the fraction bar. So this particular function has 2 transformations. They're both related to adding, though. Nothing is being multiplied by my parent function. The parent here, by the way, is 3 to the x, which is a function that is exponential. The base is 3. We know that our exponential function has asymptotic behavior to the left at y equals 0. It approaches 0 from in this direction, and then crosses here at a key point 0, 1. Actually, I'm going to move that over here. And then keeps growing exponentially, but the next key point is when we reach an x value of 1, it's going to be at 1, 3 to the 1, which, by the way, is just 3. That exponent of 1 gets made invisible, and now we have the point 1, 3. The key point here is always 1, your base. So anytime you go to the right of this key point by 1, you can find out how high that is up off the asymptote, and that will tell you your base. So I'm getting ahead of myself. So this is the parent function, p of x, which is 3 to the x. I'm going to change colors and talk about those transformations. So now this x plus 2 is a horizontal translation or shift, because it is modifying my x before I make a shape. I'm going to have to do this math first when I plug in numbers, so I'm going to do it first when I think about the transformation. The x plus 2, when that equals 0, I should get 1 out of this function. 3 to the 0 makes 1. I'm trying to find the new home of that point because it's not there. Do I have a backspace? I don't think I do, but it is not there. Let's find out where it is. I'm going to subtract 2. It's not equal anything. Subtract 2. I get x equals -2. So I have shifted to the left by 2. I'm going to come over here to -2, and this point is going to shift that way. And I will have now the point -2, 1. It's my new key point. Not the origin, but the previous x equals 0 solution. So this is my new key point. My whole function sort of shifted in that direction. And I now have this steepness going on, which means if that's just a shift, over here at -1, I will be up here at 3, because relative position go over 1 and up from the axis 3, from the asymptote 3. I would go over 1, up 3. So I have the point -1, 3 on my graph now, but that is just this part of it. That's just the horizontal shift, and I can graph all my y values, but here's the kicker. My very last transformation here is the vertical shift. So I'm going to use a different color. Let's use black just to make it nice and bold. If I take all of these y values and add 5 to them, that means everything that was here is now 5 higher. So this goes from -2, 1 to -2, 6. -2, 6. I wonder, yeah, look at that, -2, 6. And this point goes from -1, 3 to -1, what's 3 plus 5? 8. 8. But this asymptote, this y equals 0 asymptote also gets to add 5 to the y. So my new asymptote is now at y equals 5. Because when I shift the function, it shifts all of its behavior, including its end behavior here. So I'm going to approach that asymptote, and I'm going to shoot up exponentially through that point. This was -2, 6. This was -1, 8. And now I have a few key points to sort of place my graph on the paper. Now, if I wanted to find the y-intercept, for example, I can still find f of 0. I can plug in a number to my actual function and show that it works. I can plug in -2. Plug in -2, I get -2 plus 2 makes 0. 3 to the 0 is 1. 1 plus 5 is 6. -2 led to an output of 6. So when I put the input of -2 here and the output of 6 here, it's true. So that point does in fact fall on this function. I want to know what the y-intercept is though. So I'm going to put 0 in here. 3 to the 0 plus 2. That's the math I have to do first, even if there's not a parenthesis. Plus 5. So now I have 3 to the 2 is 9 plus 5, because 3 times 3. It says take 1 and multiply it by 3 twice. And then 5 plus 9 is 14. So I would have the point 0, 14. There's my axis. This is going to be the point 0, 14. It grew quite quickly. So I kind of launched off my board here. But yeah, so that is graphing by identifying transformations in their positions, right? When it's inside the function modifying x, that's a horizontal shift. The interesting thing about the horizontal shift is we're talking about, this is to the right, right? This is to the left. That's important. L for left, right? This one's not an L, so L for left. But also, when we shift to the right, our new x value is positive, which means we have to subtract it. So this was x plus 2, and it moved to the left. So when we see x plus a number, we're going to be shifting to the left because the 0 of this is negative. If we see x minus a number, the shift will be to the right because the x value that makes it 0 will be positive. That's important. So if we see anything in any of these groupings that is x minus a number, we're going to be shifting to the right to that positive number that makes it 0. When we see x plus, we'll shift to the left to the negative number that makes it 0. So what that would be these or this, right? Or underneath the fraction bar, or inside the greatest integer, or up in the exponent of an exponential, or inside this log. Okay. So now I need to know how to pull that information from the graph in order to generate the function itself. Again, we can look at this x plus 2 and say that is a shift to the left by 2 because my new 0 will be here. I want to show you something. X plus 2 equals 0. Oh, I just did that. Sorry. I'm showing you what's already here. These two equations are equivalent to each other. The whole x equals negative 2 is equivalent to x plus 2 equals 0. When I'm pulling the information from the equation, from the function definition, and setting it equal to 0, I'm solving for the x value that I'm going to plot. Well, if I have a plot and I know that my key point that's 1 above my asymptote, because my key point is always 1 above my asymptote, when I grab that key point and I see that it's at x equals negative 2, I can rearrange this equation to rediscover what must be in my function, the expression that turns into 0 when x is negative 2. If this is my new 0, x equals negative 2, I can rearrange that to get the expression that will be in my function. So this is what I want to see. I'm going this way now. I'm starting with, I know the number. What's the expression that gets me 0 when x is that number? I can both ways. Okay? If I understood the process to go from here to here to here, then let's go backwards. If I know from the function that my key point is at x equals negative 2, then I can generate what expression must be inside my function. P of this will be P of 0, my new origin or my new key point at x equals 0. I'm going to pick a different function. We'll graph it. We'll see what we can do with it. So if I have a graph like, let's say it does this. and then it does this. So we can see that asymptotic behavior. It's pointing in opposite directions and kind of seems to be following a line. So we draw that asymptote. When we see this graph, we look for the asymptote that's a vertical line that misses both of the functions. Can't go through them because the vertical asymptote is a hole in the domain. So if this is x equals -3, and then we have another asymptote that describes the end behavior, let's call that y equals 2. Yeah. Okay. So we've got this function. Now something that I can't do because I don't have a grid here very well is count out the points that are going on here. But what I want you to notice is that when I'm here at x equals, well, let's look at this point right here. I'm going to even highlight it bigger. I'm going to make it blue. This point right here, I'm going to tell you that it is -2, 0. Okay? So the rest of the grid's not there, but I know this point -2, 0, and that's going to be, you know, you might be given these red lines and you can get that point off of this graph. Okay, first step, step 1. This is close to step-by-step directions as I usually give. What is the parent function? Well, the one that has these asymptotes, this asymptote is generated by dividing by 0. So the parent must be 1 divided by x. It's really the only function with division in it. It's the only function with division in it. So if dividing by 0 leads to vertical asymptotes, then it's gotta be the one that divides. Okay? That vertical asymptote, it exists in two corners of it. This one also has a vertical asymptote, but it's from something else, and we're really not going to study that one. So here's a tip to the wise. That one's not on the test. We will study that in depth in college algebra. I wanted you to see what it looked like, but it's not on the test. So -2, 0, we have this. Oh, but normally in this function, let's graph that parent. We'll make the parent purple. Normally, we would go over 1 and up 1 here. We would have the point 1, 1 and the point -1, -1. Now, you might notice I accidentally defaulted to drawing it on the asymptotes instead of drawing it on the axis. That's because when I move the asymptotes, I also move the function, but the relative positions don't matter. Scratch that. Reverse. The relative positions are the only thing that matters. I need these to be in these corners to be the parent simply shifted. I can identify the shifts right now. I can do that first. So let's do that. Let's do a shift. Let's talk in green because we have a horizontal shift to the left by 3. So that my new x-axis is x equals -3. I'm already going to go ahead and say, well, that means that 0 equals x plus 3. That's going to be relevant in a minute. So as soon as I write down that my new origin is at an x value of -3, I'm just going to go ahead and generate that important expression. Now I've also got a vertical shift up by 2. This one's just really straightforward. That means after I generate the whole function, I'm just going to add 2 to everything. Because wise. Once I do the thing that makes the shape, I'm going to shift it up by 2 by adding 2. So I can say that k equals 2, and my x minus h here is going to actually be x plus 3. So I'm starting to see this. If I think about my parent and I want to transform it, I'm going to throw this x plus 3 into here, and I'm going to add 2 to it. Now I got to think about what other transformations might be here. By the way, my parent is the 1 over x, so I can replace p of x plus 3 with 1 over x plus 3 because I know exactly what my parent is. P of x is 1 over x, so p of x minus 3, or x plus 3, is 1 over x plus 3. This is the reciprocal function shifted left by 3 and up by 2. Left by 3, up by 2. But normally then this point here would be here, 1 over 1 up. But it's not. It's 1 over 2 down. Oof. How can I modify this so that instead of every time I go over 1, I go up to 1, I want to go over 1 and go down to 2. Well, first, I hope you see that that's a vertical reflection. Instead of going up to this function, I want to go down to that one. And then instead of going down by 1, I want to then stretch that out. I don't want to shift my axes, so I have to do something other than shifting my axes. The other choice is to pull it until that point falls on there. So I believe we've figured out that we have a negative times 2. A negative 2 times my function will take this original parent. Let me get rid of all this stuff. It'll take this parent that had been shifted and reflect it, that's the negative, and then stretch it down so that this point falls on negative 2. This part will do the same. It will reflect up to here and then stretch up to here. Reflect, stretch. So if I need to describe this, I really should say it is also stretched vertically by 2 and reflected across the y equals 0 line. I turned all my y are positives into y are negatives. I turned all my y are negatives into y are positives. Now, in order of operations, technically I shifted to the left, then I stretched it by 2, then I reflected it by multiplying it by negative 1, and then I pushed it up by 2. So the order of these is maybe 1, 2, 3, well, all right, I lied. This is 1. That's always the first one that happens because it's in the order of ops. When I plug in a number, that's what's going to happen. But 2 is this one, 3, okay, 2, 3, and then this last one is the vertical shift up by 2 because again, PEMDAS, P, do this, also in parentheses, M for multiply by negative 2, and then A for add the 2, PEMDAS, when we're plugging it in. So this is my function. We've figured it out. We've taken this red graph, I should have called it red, my function. I mean, do you want to see it on Desmos? Let's take a look. Negative 2 times 1 over x plus 3 plus 2. Let's go to Desmos and see what happens. I'm going to turn that off. Y equals negative 2 times 1 over x plus 3, and then out here, oh, there it is. It's already been shifted over and stretched and flipped. We missed our plus 2. Look at that. The point -2, 0 is right here. There's an asymptote here that goes through y equals 2. There's an asymptote right here that goes through x equals -3. So here's my new origin. It's the function. That's it. It worked. So play with that. Have somebody secretly make a function and have you figure it out, right? But please, I just play and then bring all your questions to the review on either Tuesday or Wednesday. The test isn't until Thursday or Friday, depending on which period you're in. Okay, I hope that helps.